got it. All right, thanks everybody. Hope you're enjoying your dessert. As Omar mentioned, the first year, 2016, was really just playing with clay. 2017 was the first time that we actually brought ideas to the table, right? And as I mentioned when I introduced myself earlier, we had the fortune of being involved since 2016. And in 2017, they even let us have our own team. We had the Walter P. Moore team, where we created something. I'm not sure if it actually was intended to look like that, but we created something. And we haven't had a team since. So I think it's because we were a little bit too dangerous with the tools. There were people drilling into the terracotta with the drill facing them. So I'm hoping to, maybe another year we can have a team again. But, we've been proud to be involved in this project, and we've also been in this conference and this event, both as a sponsor, but also as an engineering collaborator. So since we lost our right to have our team, we got involved in other teams, and this is just there's dozens of fantastic projects that were happened over the years, and these are just a handful of the ones that we were involved with. But the most important one that we're presenting tonight is the one that I'll let Stan sort of give the intro to, especially at the start here at ACAW.
Yeah, and just to support what Erik's saying, I mean, so much of this workshop is about collaboration and sort of the diversity of everyone that's here, and that was the case for ACAW 2017. And what you see here is our first study where we had the project sort of in a pause. It was between milestones. And we sort of needed something to bring to the table to explore, and so we actually took some of the geometry from this building in schematic design and really actually kind of amped it out even more. So like the building never really had shifted rows of geometry. It never really had forward and leaning and twisted sort of surfaces. But we sort of used the workshop, as I think a lot of us do, to kind of play with the materials, see where the limits are. And learn the processes and really push that with the team. And so, yeah, here we see the pieces that were curved and like testing out the curving of them and the size. Really, even like the notion of cutting these afterwards. And as you see with the project, it's gone through like a lot of optimization before it came to a final system. So the project, Orange County Museum of Art, is located in Costa Mesa. And that's just south of Los Angeles, about an hour. And it's located in the Segerstrom Art Complex. And if you've been there, this art complex is it doesn't really have a central sort of hub or focus, but it does have this sort of Richard Serra sculpture located sort of in the middle of this yellow zone there you see. The building itself did not need any parking. There was off-site parking. So we were able to really exploit the idea of the pedestrian access and sort of creating this new sort of gathering place for the complex. And once again, sort of the Serra is like this sort of connector and a focal point to the entrance of the museum there on that side. And the elevated plaza, so we also had this notion of a large open terrace, which was the majority of the site surface area, all the galleries below, because we didn't have to have the parking. And you'll see at the front of that sort of a grand stair to sort of invite the public in even more. The notion of nature, so the elevated green spaces, essentially a large, long, linear planter box that housed cathedral oaks, and on the plaza itself we had some palos barbreas that had really shallow soil depths. But essentially the notion of like the terracotta really being this continuous sort of cladding. I mean, there was when you look at the early renderings, you see this notion of continuity in the form. And really kind of a lyrical expression of the form itself. At this point in time, we didn't really have any notion about what the material was. And really just kind of working, as we do in these early stages, more with the planning and sort of the intent of everything. Here you see the level 1 gallery space, and on the bottom of there's a street which borders and a sidewalk, and we call this sort of like the window gallery where pedestrians could sort of look in and were separated within from the outside by these sort of long walls that further define the gallery spaces. So, just to move on, the notion of the cladding was always meant to be very continuous. So here you see it coming into the actual interior space. And as well, looking the other way in the cafe, it's constantly there. And, once again, the notion of sort of a really exuberant space and that the facade would sort of like work to convey this. We had the team under OCMA, which was, the design team was Morphosis. We had been working with Boston Valley early on in talks and talking about the systems and if we could really use terracotta. And of course, Walter P. Moore, they were our facade engineers for the whole of the project and really critical in nailing down this backer structure. Because as you'll see, it's really about like a full holistic system as far as how the terracotta actually is on the building at all. Clark Construction was the GC who won the bid, and underneath them we had Beck Steel out of Texas, Radius Track under Infinity Engineering, who's doing all the cold form complex light framing, and then we had Best, who was sort of the prime on all the install, right? So they were teamed up with SFS Engineering, who developed all of the sort of support points in the subframing using the envelope system. And of course, Boston Valley Terracotta, who was working with us to optimize and come up with the clay solution. Roschmann Group out of Germany actually ended up with the glazing, and so we had some wins there. They brought together some good acumen as far as doing structurally steel-supported glazing systems. And we really tried to make this building a really sort of elegant and streamlined and knitted sort of a system of enclosure, enclosure systems, even though it had so much sort of aggressive geometry to it. So of course the surface model. So we use this surface model to sort of define all the different systems in the building and use it as sort of like the digital database for documentation, visualization, analysis, communication with consultants and whatnot. And so, obviously the drawing set and scoping things out. On the top, you see the scope of the exterior atrium terracotta. Then below that, the interior atrium terracotta. And then the long sort of bars at the plaza. And these other elements are exterior as well. But really trying to paint the picture of simplicity, right? So anything that you have that's really complex, especially in the documents, you really want to convey a notion of feasibility, that things are worked out and really for our own good, right? That the design intent's going to hold up and we've got some ammo in construction. And then, so this sheet is typical as a system sheet for terracotta, and the final system actually having units that were planar, and curved, and ones that were fully curved. And we'll get into a bit more of how it's all rationalized, but really kind of scoping out the building and the systems, and really going with a very simple cladding detail, which was inspired off of a very typical TerraClad system, a rain screen system that Boston Valley has developed and used on many, many buildings. And we really kind of looked at this as the way to success, because we really couldn't afford to have any sort of unmanageable complexities in the terracotta itself. And this whole notion of a simple offset geometry set out for all the layers in the wall was I think really critical to success. And so obviously all the typical details running through all the conditions and eventually into the interface. So here you see on the left, it's basically a cut through the curtain wall, which is, here you see the end condition where the T looks like an L. And really that L is single curve to match the terracotta interface, as well as the legs that you see extending out the back, which are pattern cut steel plates welded to the L's, which actually just mitigate. It's almost like a sort of closure for that complex interface. And once again, the same details that kind of roll up onto the atrium skylight, which is on the right here. And so with that, I'll let Erik get into a bit more of like the secondary steel design.
Thanks. So, as Stan mentioned, our role in the project was enclosure consultant. But when you're working, we had the fortune of working with someone as technically savvy as Stan, who knows as much or maybe more as some of the people on your team. Our role became more of sort of enclosure engineer, where we were using our sort of structural engineering skill set to assist in the sort of development and creating a really integrated system. So our team, which was led by Kais Al-Rawi, who couldn't be here tonight, so he gets most of the credit for our team on this project, really worked with Stan and his team to develop the secondary structure that supported both the glazing as well as the terracotta systems. And so what you see here on the screen is sort of, the generation of both the terracotta backup steel as well as the glazing steel, and the sort of type of output that we would produce and that ultimately fill into the set. So while Stan was busy developing, the kind of technical details and the architectural sort of drawings that represented the enclosure systems, in this case, this is one of the facade. We were busy doing the kind of engineering behind those systems. And so for the glazing systems, just to touch on that really briefly, since it's not a focus, this presentation not focused on the glazing, more on the terracotta. The glazing system wanted to be really minimal. It wanted to be long spanning and, transition from glazing, vertical glazing into skylight. So what was proposed was a steel T-profile system, very slender. That one was, ultimately engineered by us, and the documentation that we produced was, fairly straightforward. It was a system of diagrams that indicated the type of member size, the connection, the reactions back to the base structure. And so here you can see an image of the shop drawing that represents that. The steel, the way that the glazing was secured to that T-profile was through what we call an add-on system or a veneer system, which is essentially just the front face of an aluminum profile. And that glazing would be attached through a toggle system to create a sort of structural silicone approach. As opposed to using structural silicone, a toggle was used instead, so that the securing method was buried within the joint. And what you can see from these construction photos is that there's this process of engineering and detailing and back to engineering and detailing was all in an effort to sort of create the sort of most integrated approach to the interface condition between the glazing and the terracotta skin, which existed both on the outside as well as the inside, as Stan mentioned. So in order to do that, we created what we call coupled models, which is essentially these centerline models that were generated from Stan's team's surface model that represented the center lines of all the steel geometry. And that steel geometry was both for the terracotta, as you see in this sort of more blue and purplish color, and the glazing system, which was represented in green. And we had to do that together because the systems were fully integrated. The steel system was actually secured and fastened directly to the steel system of the steel system of the glazing was secured to the steel system of the terracotta. So those center lines were analyzed, output again as surface geometry that was then input and integrated with the structural models as well as the architectural models, just to make sure that integration and that sort of coordination could happen very fluidly. And you can see here how an overlay of the glazing system with the steel of the backup steel of the terracotta, and how one relied on the other. And here you can see a zoom in where on the upper right, you can see the orange steel members. Those were the secondary structure for the terracotta support, and you can see that represented here in the detail, and the glazing system coming in directly to it. So as Stan mentioned, a lot of those systems were sort of just knitted together, right? And then the air and water continuity kind of happened on top of that. Again, overlaying all those different system types, just along with overlaying with the surface model to make sure that we got as much integration as we could. And then again, folding that into an output, which is a series of documents that ultimately the contractor used to engineer their systems and design the details and the connection details, as well as using our centerline model for the fabrication of the members as well. So again, these details were fairly straightforward, or these drawings, but they represented line drawings with end support conditions, reactions, and member sizes. And you can see here just a shot with construction where the steel, you can see how complex the steel was, right? And this was all before any cladding went up or before any infill of the light gauge that radius track provided went in, and really sort of kind of the impetus for the next stage, which was the patterning.
Right, and so this is kind of like a fast forward to what we ended up with the patterning, but you can see how this really is a sort of like a very clearly an offset system, right? And there's just layers that are offset in geometry that are really readily controlled, and it really the task was then how to bring the loads back to primary. And we worked with John A. Martin and Associates in design with Walter P. Moore and really fine-tune all these movements, right? So we knew that like the head of the classroom that was cantilevered had the curtain wall spanning across, and that there was movement between that and the main bar. We didn't want any joints in it, so we designed all the systems to be able to take incremental movement across a large distance so that any sort of significant movement would be insignificant as the system sort of flexed. And as we get through this, there's some poignant things I can point out later to that end, but we'll get into the construction now, and here what you see is the Clark Construction's construction models. So now this is with Crosby Engineering, having looked at the engineerings and the sort of like the ladder concept, and really not really adjusting too much because it essentially worked. As much work as there is still left to work out the connections and whatnot. This represents sort of the blue, the original members, and then these sort of different colored members were the ones that moved. So the yellow was the new position, the purple was the old. So these are relatively minor moves based on connection detailing. And so what that means is that we did a pretty good job. Like we're not really fighting about form, right? When we're talking about resolution and not adding more steel. And once again, this is kind of like, I guess, a stage where we have all the secondary steel up, none of the glazing is going up, but you can really kind of see this sort of zone where I'm talking about where the curtain wall goes across and there's this potential movement. And we sort of managed this so well that, the glazing with that toggle system performed. And typically with the structural ceiling glaze system, it'll just flex and no problem, but I think there's a lot of attention in CA to make sure that that toggle system worked. Materials research, right? So we're sort of like, at the mercy of how long it takes to do clay prototypes at 1-to-1, right? So we're gonna do it out MDF. And, we're just gonna look at it, and here we're looking at open joints, and the notion of a 5-foot long, roughly almost 2-inch thick extrusion, and what the jointing should be. We wanted an open joint sort of system, and we also wanted to sort of have a system that really was sort of, like understated in a way of the jointing, right? So you can see that the horizontals are really kind of suppressed. I'm sorry, the verticals are more suppressed than the horizontals, and so that kind of goes back to the original sort of banding that you saw in the visualizations. Like here, clearly we're seeing that we're not stepped anymore, that we've gone to sort of more of like a coplanar with a design surface assembly. Looking at the different material palettes and clay bodies as well as glazes, but in the end, we settled on a pretty achievable and popular, I guess, combination of like the cream and the white glaze, which is pretty standard and pretty funny. But I think in the end, it was so much of it about the project was about the form of the building, and I think that the glaze was something that was appropriate, with the sort of fine texture that we had, mimicking sort of the larger texture. This is a sort of render out of our really early schematics, and this was coming at a time when we were really starting to question the idea of, well, what is a system? Is it stepped? Is it like a regular stepping? Is it, shingled. We looked at many things, and at the same time looking at materials. So we're like costing all these options. And here you see one rendition on the left that could be GFRC, terracotta, what have you. And so those are the things that we priced: terracotta, GFRC, metal. And in the end, coming up with some schemes that dealt with the stepping. And really the metal, surprisingly enough, this is pre-pandemic, but coming out actually quite high in the scheme of things. And so this is where we really started getting into ideas of how we could really tackle this and optimize with Boston Valley. And
yeah, so when we got back involved with this project, Stan approached us, and this is a rendering from the first model that was given to us. And you can see that there's basically 3 major die heights to it. So there was I believe it's an 8, a 10, and a 12-inch course height. And so looking into it, they're looking for us to provide some early numbers to just get an idea of where they're going to be running for the budget. So given the level of information they baked into the model, we were able to run some scripts and basically evaluate the model more or less in Excel. So we didn't actually have to go around and understand every component individually and spend the time to compare it that way. We could run some scripts. And one of the first things that we really noticed was the walls, as they cant in and out, they were trying to keep these horizontal water lines. And as the walls cant in and out, what that really forces us is we no longer have just 3 die types. Every wall has its own kind of unique die coursing so that you can maintain those horizontal striations. And that was something we brought to the team and said that's going to really drive cost. And there's ways that we can start to look at how to eliminate that. So then Stan and his team came back to us and said, well, what if we were just to switch it to 1 standard die height? Can we do that, but still keep our horizontal wire lines? And we still ran into the same issue. And so we went back and forth for, I'd say, quite some time actually trying to figure out how can we achieve this water lines? Can we play with the joints? Is it going to be noticeable or discernible enough or not? And then I'm not sure who it was on Stan's team, but someone came to us and said, what if we'd force it to be 1 die height, a 12-inch nominal height, and we follow basically the ruling lines of the geometry? So I'll let you get back into that part.
yeah, and so the funny thing is it has to do with, like the listening to the geometry and almost like listening to the material more or less and what it wants to do. And so we clearly understood that all the geometry was developable, meaning you could flatten it. So like it's made up of cylinders that are tilted, which are in tangency with just straight planes. So you only have straight planes and you have cylinders, so in theory you can flatten those. And so here's a surface model with all the continuous terracotta pieces isolated. And what we had done was essentially to flatten this, like I said, and then quite literally apply a grid on top of it. And then once we had done this, we kind of knew where the lines would be on the surface, or where they wanted to be, let's say, and then we rolled it back up. So in doing so, you kind of understand that, well, now these pieces are essentially, can be constructed from just 1 type, essentially. At least 1 extrusion type.
Yes.
That yields many, many types, but at least it cut out a lot of the complexity. And what you see here is not as simple as me, saying that, the team unrolled it, put the grid on. It's a highly manual sort of act, and very sort of hand as far as how the panelization was sort of massaged and optimized visually. And in the end, we sort of took this and finally developed a design surface model with the final panelization. And this is when we kind of got in touch with Andrew again and said, hey, look, I think we got something, and let's run some numbers on this.
Right. So the first thing that Stan brought to us then was a 60-inch long module. So that's our maximum length, if anyone's not aware of that one. And so that basically minimizes our number of attachments, which is great for the facade and everything else that way. As we start to really look at it and evaluate the surfaces, especially the areas of curvature, curving a 60-inch long part across a fairly tight radius, I think we got as tight as like a 30-inch radius, that becomes a very tall refractory form to try to support that, and that really hinders our throughput. So we started talking with Stan and saying, you know what, a 30-inch module would really work better for us to get through the facility in a timely fashion, because construction is all about money, but also time, right? They always are intertwined together. So then we started to look at a 30-inch module, and I think there was some reservations with this one because of the introduction of a lot of those vertical joints that Stan was talking about in the previous material test, that they start to become more prominent. So wasn't super keen on that one. So, but we thought we were onto something with the round areas and making those pieces manageable for us to move through the facility. So we started to work on a rule set with them to say basically these are the minimum dimensions that we have to meet for certain thresholds. How do we really optimize this to minimize the number of unique parts while still achieving the design intent? Because that's the last thing we want to do, is really destroy the design intent. And I think Stan's team was really successful with following these rules and generating areas of curvature where we would use 3, maybe 5 different forms to create that curvature and then transition back to the planar surfaces. And then after that transition, they were still able to keep that random running bond look. So this is one iteration where there was a fair amount of the blue panels are your 60-inch panels, the greens are your 30-inch panels. So they started to look at the different patterning of the schemes. And as we started to talk through this more, we realized that construction tolerance has really become an important factor for us to factor into this, right? So we're designing everything from a surface skin, but how do we accommodate for construction tolerances? As much as we want to say everyone's perfect, we know those are going to exist somewhere, somehow, so how do we accommodate that? So what we started to work with was saying that the cylindrical areas were the driving geometry for it, and then every course would have at least one shorter panel integrated within it so that the contractor could adjust that panel and integrate into the facade and keep it working together. And then Stan's team, I think rightfully so, saw that opportunity to also introduce some other panel sizes too, just so that those smaller panels don't stand out like a sore thumb. As we were talking about that, the construction tolerances, the edge conditions came up, right? Because the panels are not just a linear piece, typically horizontal or vertical on facade, but they're going at all different angles. So how do we deal with the edge conditions on the facade? Because some of them came to very fine points. So we could produce those, right? So we can produce a shop drawing, cut them, it'll work great. But if the building's off here or there, you're going to get a stair step look. It's not going to be precise. And when we start to really catalog it more, again, running some scripts to understand what we're really facing, we were able to break it down and understand how many curved panels there were and start dialogue with the contractors to say, actually, what we think is going to be best is we're going to provide you with standard modules. The standard module will cover 90% of the facade, and then you can deal with the edge conditions. So if there's this bust here or there, it's no longer a bust because you just follow the design guidelines that Morphosis sets, and you can trim the panels in the field to produce the panels. So from there, we were able to basically generate a very specific list of the different geometry types. And from there, we were able to put a budget and actually a hard bid together for this and win the project, because we had all this built-in knowledge on the project. We knew we'd be very successful on it. And then we could move into the mock-up phases once we were under contract. So for us, we did a mock-up of the tightest convex and concave area. And we did that just to make sure that we had the right proof of concept to show the team that we would be successful with this project. And here's an example of, this is our mock-up that some of you may have seen out in our driveway this morning. And some of the details with the adjustment that we built in, again, to accommodate those design tolerances or construction tolerances that you can't really get away from, but you have to live with. So then Best also built their own.
That's right. So we have an identical mock sent to Best Construction, who constructed that at their shop so that the team in Los Angeles could evaluate the same construction. And I think what's important to point out here, and the main reason for why I think you guys really got the bid, was the fact that you were able to achieve this challenge between the half curves and the planar elements, and that was a huge thing, right? Like, because no one wants to see those joints just come rifling through the geometry. And as you can see here, there would be two diagonal joints just flowing through here. So this was, like, I think, a really huge aspect of the clay forming, and one of the challenges that Boston Valley really came to a solution with. And, you know, very much part of the mock-up was also testing, field testing these. In here you see a field test of a mitered corner panel cut, some earlier sort of design confirmation sort of models that went along with how, you know, SFS was going to finally engineer it. And what we've got here is basically the concept sort of sketches of the planar system on top, which is actually pretty orthogonal and understandable, right? You can see it there in the picture in the middle. Just some clips that hold off some T angles with some continuous girts. And, you know, the rule with all these masonry anchors is it has to hit 16 gauge steel, right? I think earlier talks with Walter P. Moore, we were always talking about should we make it a solid 16 gauge substrate on the curves, but that was something that we talked to the GCs about even early on, and it was something that they said that, well, we probably don't need it. In the end, we ended up putting so much strapping in here that you can see that just to bridge across so you had places to screw into. It could have almost been solid. But, you know, the visual mock-up was just like so key in giving the team and the client confidence that, you know, that Boston Valley had licked the clay. You know, Walter P. Moore and Morphosis were then kind of, you know, really kind of like set up with all the components to like make the whole system kind of work. And you know, more shots of the sort of curved, you know, you see how it's sort of a modification of the orthogonal system, but intrinsically it's the same system that's just rolling around the entire museum. And so, you know, a big part of this is mock-up and testing, right?
Yeah, absolutely.
So,
You know, those mock-ups that Stan and Andrews presented were proof of concept with really just maybe one or two kind of players involved, right? When we scaled up to the performance mock-up, we had a number of different players. We had steel contractor, we had the framing, the light gauge framing, we had the terracotta and its clip components, as well as the glazing and the steel support for the glazing. So it was really a Frankenstein sort of mashup of different systems, which is really the kind of the true test of how all these would work together from a performance perspective, but also another proof of concept to make sure that we can properly get trades talking to one another that are from, you know, in their own different silos. So you know, what this mock-up represented was a mashup of the terracotta corner system, the atrium glazing in both its sort of sloped and skylight condition, the shingle the single layer glazing that's underneath the sort of overhangs of the terracotta, and then the curved girt systems. And so this was tested for air, water, seismic, and it allowed us to test, you know, kind of for two major objectives. One was, you know, the interface conditions between the multiple systems, and then also those sort of performance criteria of air, water, and seismic. So, you know, we learned a lot from this process of doing the mock-up. You know, there was a lot of things that we learned in regards to compatible materials and what materials could be eliminated potentially that may be causing trouble. It taught us a lot about, you know, conditions to look out for when multiple trades are working together. So there was conditions where, you know, the glazing supplier put a hole in the sealant, you know, next to the terracotta, right, or the air barrier, and so we learned from that, and then also through the, you know, the glazing installation, you know, we had to you know, that add-on system of the steel T profile is a very unique system that isn't that is not done very often in the United States, and so installing that takes a lot of knowledge and practice. So the steel and the glazing were rebuilt twice just in this mock-up just to get it right. Even, you know, learning to make sure the glass is installed the right way, right? Where you see this sort of purple-looking glass right there, they sort of installed it backwards. So a lot of things that we learned from the process of this mock-up. Oh, this was video. I did not realize it was a video. Again, you can see here, you know, the sort of level of detail that went into sort of the integration of all these sort of brackets that supported the curved terracotta areas, right? And how each one was detailed in a way to limit water infiltration. Learning that, you know, certain parts of those, like the green thermal isolators you see there, actually caused some issues. So they were eliminated in the end. And ripped off and redone. So a lot to learn about with the mock-up, and that's why, you know, we also often argue, especially in projects this complex, why mock-up should be done.
And so simultaneous with this sort of the performance mock-up, what was happening with Boston Valley, we were really getting to the point now, really tackling all the kind of really special conditions, right? And we had a few special cases here.
So there's a couple, right? So where you get slivers, and even if they were to cut them in the field, it probably wouldn't come out precise. So we had to come up with a couple of unique solutions for a certain area. So this was one area, kind of at the peak of an eyebrow, where we actually made a double height die. So it was a more costly approach to the solution, but I think in the end it provided a better aesthetic approach than trying to have two pieces come together to basically be razor thin and not really last on the facade. We also had areas where we had super tight curvature in the panels, where actually most of these panels, right, they were slumped across a cylindrical object, mostly along its longitudinal axis, so would be very successful in bending them. But we did run into a couple of areas where basically they were slumped across the latitudinal axis, so the narrow, more hot dog, if you will. And those were pieces that, trying to bend, you're really increasing the tensile forces in the clay, and we knew we would not be successful in trying to slump them and achieve any sort of tolerance with those pieces. So what we ended up doing was actually moving to one of our other forming methods. Instead of extruding them, we elected to slip cast a handful of them so we could provide the design team with their intended look, however, manufactured in a way that we knew we'd be more successful with. That also led to some of these, so here you can see some of those slivers and the issues that we were coming up with there, and working with Best Construction on how to anchor some of these pieces, right? So all the clay panels, you always want to have 4 points of attachment. Some of these slivers really get into really narrow pieces, and they might not be able to achieve that. So talked about mechanically attaching them. How do we make sure that that works successfully when you have such large joints in between the units so that you can't read them? And really working through those sorts of details. How do we make sure that it all comes into conjunction? And then there was also a question of basically fabrication methodology versus idealized geometry. So I'll let you talk to this one a little bit more.
Yeah, so as I said, you know, the design's geometry was essentially planes and cylinders, right? And being an offset geometry, in the way we modeled these clay pieces, we simply offset things, right? And you think about, you can just lay it on a sort of cylinder and fire it, right? But what we came to understand, and through some education, was that, you know, the different sort of surface tensions or the qualities of the clay piece as it gets fired, it just really does not want to do that. Right, and so there was a more sort of achievable way of forming, which is more akin to sort of a twist, which is also like a ruled surface, right? Only it's not developable. But then when you're dealing with a sort of plastic material, I guess that's kind of inconsequential, right? So then what really comes down to is like the tolerance, right? Right. And some of these units you see here, we have overlaid. That yellow is the design surface, and then this sort of mass is the actual solids shop drawing model that we got from Boston Valley. And here, you know, the deviation is 0 inches on this, like, in this, you know, the tolerance of 16th inch. Our biggest bust was 5/16th inch, right? But this thing was hanging up behind the back of the reception desk or somewhere not visible. There were some other pieces that shared this same kind of tolerance bust. And we were working with like really tight tolerances. I mean, we were saying 1/8 inch was the limit, right? And I think from
right. So, and in order to achieve those, that's why we went through and did some internal testing, both with showcasing, I guess, how we were proposing to produce these pieces, as well as producing it based off of the idealized geometry to kind of show why we want to take the approach we did, and how that approach really impacts the jigs, how we fabricated, which ultimately is what drives the accuracy of the panel geometry. Because without those jigs, right, everything's working from that design surface and offsets from it. Our jigs are actually supporting the back side of the panel. If they were to support the front side, we wouldn't be able to glaze them. So we had to support them from the back side and had to telegraph that back through to the front side to achieve the end result. So after the internal testing and moving forward with the more twisted sweep approach, we then also internally had conversations about, okay, how do we prove that these pieces are within tolerances? We know they're going to be within tolerance, but we really need something that will substantiate that and give everyone confidence working with the material that they can install it in the correct plane, and everything then truly does still remain as an offset surface geometry for the entire wall construct. So we got a 3D scanner. It's basically a CMM, so a coordinate measuring machine with a laser scanning head, and we scanned every single piece of curvature on the OCMA facade, and then compared it to our digital model to understand how accurate that piece was. And we could understand the accuracy through basically the heat map that you see on the right-hand side. So this piece, its greatest deviation was less than a 1/16 of an inch, which, given the complexity that this terracotta is going through, is absolutely phenomenal. And all the pieces basically were at that level for the facade. So if you go visit it now, it's an absolutely breathtaking facade. And I'll let you get back into some of those details about attachment.
Yeah, so SFS engineering was going through each support condition for every panel. So that means each panel, a minimum of 4, had to find a stud. It had to have ample support based on the orientation. At times it was just dead load and wind load anchors, but you can imagine when it goes vertical or diagonal, you start to get many different combinations. So SFS did an amazing job of going through each one of these things, and when they're ready to send us the model and told us so, it became a very daunting task to imagine us kind of going through every single clip and making sure that it was every piece was supported. So we asked for more like kind of typical details and sort of these views, which were essentially elevations which were not even flattened, but at least were noted with sort of symbols like you can see in the upper corner there, the different girts that were used, the different types of anchors that were used, and then we used that to sort of understand, overlaid with terracotta, where all the pieces were being supported for an easier review, as well as ask for the model itself to just kind of do a sort of visual check as well. And this is just like one portion of the model, but you know, every single one of these clips is actually surveyed as well. So I mean, the whole notion of you know, I think after a while the need for every single clip being surveyed was not really a reality. I mean, I think it was mostly a series of surveys, right, with the steel, the secondary steel, then the substrate, which kind of, you know, gave most of the confidence that you know, the clip system was going to just be perfectly fine. So now we can show some sort of construction progress views, and with this, and this is the view of that sort of the side that borders the street and is a sort of window gallery. You can see it. Underneath this sort of overhang is the loading dock. So you can see the whole cathedral oaks that are planted above that create sort of this kind of green space above. And really, the planter box is where we first tested out these sort of miter cork cuts, and the guys are kind of getting their sort of technique down. You know, like I said before in the my intro, that, you know, I really believe that a lot of it comes down to the hand, and this project was certainly that, as well as like a lot of ingenuity, and you know, the fact that like innovation, I think a lot of times is just born out of just appropriating things and applying them in new ways and pushing them, right? So here, you know, you see a much more complex corner. They're having really good results on the project. You can see how it's all completely continuous, and you can see how the pattern really just rides in very, very kind of dynamic ways across the facade. And to just understand that each one of those is essentially the same extrusion. Some more shots looking up at some of the corners here. This is on the back side actually, which is metal. That's with the stair that comes up it. But once again, all the corners, the guys at Best just doing an amazing job, and really the building just sort of just flowing, kind of like the initial ideas. Some progress shots of the green space above with the Palace Breas here, and a view out from this sort of multi-use gallery space up on the plaza, looking across the plaza here to create this sort of landscape. And some shots of the interior. So this is interesting, you know, all of the interior essentially, except for some areas, are supported off of stud framing only. And so throughout the course of the entire you know, surface area of all the terracotta assembly, there's actually not one true movement joint or expansion joint. And that's true for the whole of the system and the whole of the building, actually. So, you know, once again, you see kind of like unfinished. You're not seeing the coping pieces that cover all the field cut pieces. But on the left, you see this sort of plaza level view where this is a moment where actually the secondary transitions to cold form metal framing only. All the other shots, everything is essentially, you know, the middle shot is all stud framing they're supporting. The bridges, a series of 3 bridges that look up at the atrium there. And you can see how just, you know, utilizing the structural T profiles on the glazing really minimize what this 65-foot tall curtain wall requires for structure. You know, like you're really just looking at a mid-span beam, breaking that down, breaking the span down so it's achievable in thin elements, and sort of some minimal sort of detailing that we were pushing through with Roshman, who was actually lapping the T's and splicing them where we couldn't get the single piece. And you can really see on the inset, really, it's actually a geometrical impossibility, and maybe construction as well, that the closure piece on the T would knit up perfectly with the terracotta, but it's pretty darn close. And so we're getting really good results, and, you know, like, eventually we'll have a proper presentation on this, I'm sure, by friends at Morphosis, but this was really kind of end with this shot, which is kind of like one of the most dynamic kind of views, I think, looking one way at the entry and the other way. I mean, this is no fisheye lens or anything, so. And with that, actually, there's one more shot I think we can slip in, which is, you know, up at the plaza, and here you can really see the flow of the planar pieces, the planar curved, and into the fully curved pieces. And so with that, thank you.